Hi, I'm Kashish, and today I'm going to discuss question 1 for homework 10 EL6303. So, the question is that we have to describe processes like the Poisson process with respect to their probability, masses, or density, the mean, and autocorrelation. So, starting with the Poisson process. Poisson process is basically a process that is a process of arrivals or departures of something. Like we've discussed, it is the arriving of a bus, the waiting time for a train, etc. So this particular number line represents the Poisson process, and we show that x of t, say, is an arrival process. So x of t will depend on the Poisson variables lambda and t. Now when we're talking about random arrivals, it is going to be dependent not only on the parameter lambda but also on t, because the time at which these things are happening, the arrivals are happening, is very important. That's why x of t is going to depend on lambda and t. Now the expected value of a Poisson process is basically the parameters that it depends on, so lambda t. The autocorrelation function, as we know that the autocorrelation function, the basic formula is expected value of x of t1 into x of t2. So now if we had to derive this, we're going to derive it in the following way. So consider this. So just start with this. So that's expected value of x of t1 into x of t2 minus x of t1. So this is basically, and another thing that we know about Poisson processes is that two intervals which do not overlap are independent. So this is basically the interval 0 to t1, and this is the interval t1 to t2. So expected value of x of t1 into x of t2 minus x of t1. So if you, since they are independent, we can split the expected value. So expected value of x of t1 into expected value of x of t2 minus x of t1. So if you try to simplify the left hand side, you're going to get x of t1 into x of t2 minus x of t1 into x of t1, that is x squared of t1. So again, you can open up the brackets of expected value, since expected value is a linear function. So expected value of x of t1 into x of t2 minus expected value of x squared of t1. And out here, expected value of x of t1. So we know expected value of x of t is lambda t. So expected value of x of t1 is going to be lambda t1. Again, by the properties of a Poisson process, and if you derive it, you'll know that x of t2 minus x of t1, if you have a difference function, the expected value is basically going to be the difference in time into the parameter lambda. So lambda of t2 minus t1. So yeah, so we finished this part. Now this is basically the autocorrelation r t1 t2, and this is what we have to find. So how do we find this? Now we know that the formula for variance is going to help us find this, because variance of x of t is basically the expected value square minus square of expected value. So we know that variance of x of t is equal to expected value of x of t when we're talking about Poisson processes. So variance of x of t is lambda t. So the e of x square of t will basically be the variance plus the expected value square. So lambda t plus lambda square t square. Now we know the value of this. We know that this is the autocorrelation function itself, and these two are simplified. So autocorrelation function minus e of x square t1, that's minus lambda t minus lambda square t square, is equal to lambda square t1 t2 minus lambda square t1 square. And out here, what we have to keep in mind is that we are considering that t2 is greater than t1, because we are considering first an interval 0 to t1, and then we are considering the interval t1 to t2. So it's clear that t2 is greater than t1. And once we solve this, we're going to get our xx t1 t2 is lambda t1 lambda square t1 t2 when t2 is greater than t1. If t1 was greater than t2, this would change to t2, and therefore we see that it basically takes the minimum value of t1 and t2. So we can write it as rxx t1 t2 is lambda square t1 t2 plus lambda min t1 t2, and the PMF of the probability the PMF of a Poisson process, the PMF of a Poisson process is basically e raised to minus lambda t raised to k upon k factorial, where t is basically going to be the length of the interval ti minus tj. Next, we're going to talk about Poisson increments. So again, the PMF of a normal x of t Poisson process is going to be e raised to minus lambda t raised to k upon k factorial. Now you consider a lumbar line and you consider this to be t and this to be t plus c. So we know that the increment was by a factor or a value c. So x of t is Poisson, y of t is going to be x of this minus x of this divided by the factor c. So x of t plus c minus x of t divided by the factor of increment c. And we also know that the PMF is going to be equal to n by c because the total divided by the factor c. So PMF, so basically the probability of x of t plus c minus x of t is equal to n, and this will be equal to e raised to lambda c raised to n upon n factorial. The only thing that really happens here is that c is replaced by t, and the n out here is basically the total number of increments, so n factorial, and n is greater than or equal to 0. The expected value, now the difference comes in the expected value. Since we are finding the expected value of increments, we are going to divide the total by or we're going to divide the expected value, whatever we get, by the factor c, by the factor that we are incrementing it by. So expected value of x of t plus 3 minus x of t is divided by c is basically going to be lambda c divided by c. We know that it's clear to see that the expected value is going to be lambda c. After looking at this equation, we can kind of draw a relation between the two, and we know that the expected value of something that looks like this is lambda t. So expected value of something that looks like this is lambda c. But this is going to be divided by c, and that's why it's just going to be lambda, which is not a function of time or a function of the increments, which is a point to note here, because we're talking about Poisson increments, and we discussed that Poisson processes, in Poisson processes, the expected value not only depends on lambda but also depends on the time t, but in Poisson increments it only depends on lambda. Next we come to ry t1 t2. So ry t1 t2 obviously by formula is going to be expected value of y of t1 into y of t2. Again, the difference is going to be that we are going to divide it by the increments. So since we are multiplying 2, we are going to divide it by c into c, which is c squared. And so then you have an interval t1 and t1 plus c, another interval t2 and t2 plus c. So in the first case, you consider that this is t1, this is t1 plus c, this is t2, and this is t2 plus c. So basically these don't overlap. So this is a case where t1 plus c is smaller than t2, and then these two are not going to overlap. And since these two are not going to overlap, we can consider that they are independent and they are non-overlapping. So ry t1 t2 is going to be 1 divided by c square, expected value of x of t1 minus expected value of x of no, I'm sorry. First, you're going to open up these brackets. So you're going to get expected value of x of t1, x of t2 plus c, expected value of x of t1, x of t2, again minus minus will become plus. So okay, that's here. And then expected value of x of t1 plus c into x of t2 minus, and expected value of x of t1 into x of t2 plus c. Now after we get this, the working is not shown here, but since we know that these two are independent processes, you can open up the brackets. So you're basically going to get 1 by c square, expected value of x of t1 plus c into expected value of x of t2 plus c, expected minus expected value of x of t1 into expected value of x of t2 plus c. And this is going to be easy to formulate because you know expected value of x of t1 plus c is basically lambda into t1 plus c, and expected value of x of t2 plus c is lambda into t2 plus c. And then once you open up everything out here, you're going to get 1 by c square into lambda into c raised to 2. So again, c square will get cancelled and you'll just be left with lambda square. So that is a case when these two don't overlap. Now we're going to discuss a case when, say, t2 is somewhere here. That's why the two intervals are going to overlap. So we're going to discuss the case where t1 plus c is greater than t2, and when this happens, we can see that t2 from t2 to t2 plus c and t1 to t1 plus c, we can see that there's an overlap out here between t2 and t1 plus c. So when there's an overlap, clearly you're not going to be able to open this. You're going to have to leave it at this step. And once you leave it at this step, you're going to get the expected value of x of t1 plus c into x of t2 plus c, and that is going to be lambda into t1 plus c. That's going to be lambda into t1 plus c into t2 plus c. So once you open up that, you're going to get the autocorrelation function of t1 t2 as lambda square plus lambda square divided by c plus lambda into t2 minus t1 divided by c square. So that was about Poisson increments. Now we talk about normal processes. So a process is called normal if the random variables from x of t1 up till x of tn are jointly normal. So x of t1 and x of t2 should be jointly normal, x of t1 and x of tn should be jointly normal, x of t2 and x of tn should be jointly normal, so on and so forth. So basically, when random variables from t1 to tn are jointly normal for absolutely any value of n, of course from t1 to tn. So that is when a process, all in all, is called normal. So expected value of a normal process is basically going to be eta of t. Now this eta of t is a constant, and the autocorrelation function depends on t1 minus t2, the absolute value. Then this process, which is a normal process, is going to be considered White's stationary. Now talking about the first order normal processes, so we know normal processes depend upon the mean and the variance, and we also know that mean is eta of t, and then we learn that variance is basically the covariance depending on t and t. Now if you make t1 equal to t2 equal to a value t in the formula for covariance, you're going to get the formula for lambda square x of t. So lambda square x of t is basically covariance of t and t, and it's easy to derive that just by putting t1 equal to t2 equal to a value t. So that's going to be the first order normal process, and the second order normal process likewise is going to be dependent on the parameters lambda t1, lambda t2, c t1 t1, c t2 t2. Again, it's going to be the square root because lambda square is c t1 tt, and it is also going to depend on the autocorrelation coefficient rt1 t2. Another thing that we have to note in a normal process is that it is invariant to a shift of the origin. So basically, it's invariant to probably the time axis. And the characteristic function of a normal process is this. So it's the exponent j summation I eta ti into wi, or omega I minus half summation ik, the covariance ti tk, wi wk, or omega I omega k. So that's about the normal process. Thank you for listening.